So we'll just kind of talk about the some problems. The first one we'll talk about is number 8. So just establishing these rules of mounted sequences, basically. So as an example, here's a mounted sequence that we could do. So basically 1 through 13, followed by 15, and then the last one is 14. Does that make sense? So
Yeah.
what we're going to do is we're going to kind of like brute force the crap out of this. And we're going to put a little bit of assumptions onto this. Okay? So I want you to basically zero index the sequence. When I say zero index, basically whatever your first number is, that's the zeroed position, just like how an array works. Does that make sense?
Yeah.
So I want you to imagine that 15 can be in any position, position 0 all the way to position 14, which is the last number. Does that make sense? Hello.
Mm-hmm.
So for example, let's look at when 15 is in position 1, right? So that means it's in the second number in the sequence, since position 0 would be the first number. Does that make sense?
Mm-hmm.
Okay. So how many numbers are less than 15?
13?
What's up?
13?
None. Nope.
14?
Yeah,
14?
14. Yeah, 1 through 14. Does that make sense? Now, if 15 is in the first position, how many numbers need to be to the left of 15? How many spots? Assuming that 15 is in like the first position, or like index, or is in position 1, meaning it's the second number. How many numbers? Not 13. Think about, like, literally how many
No,
spots,
you 5. Because yeah, you can use
like how many spots are before 15 here? In this thing here, like how many spots are before 15?
One spot in the 0 position?
Yeah, it's one, whatever is in the zeroed position, there is an open spot. So you need to have one number that is quote unquote ascending. Well, there are 14 numbers less than 15, and we got to take one of them, right? So there's 14 choose one ways to pick the one number that should be quote unquote ascending. Does that make sense?
Yeah.
Okay. Now let's think about it when it's in a different position, say position 2. So that means it has two numbers to the left of 15. We don't look at no, because we don't really care about the numbers after 15, because all the other numbers that we don't pick to go to the left, we already know where they're going. They're going to the right side. Does that make sense? So like if I say, for example, the value 10 is going to go to the left of 15 here, what can you assume? Where do the other 13 numbers go? Obviously to the right. Yeah. Does it make sense? No, they are organized. The point of a mountain sequence is that it must be in descending order if it's to the right. If you are going to the right, you must be in a correct descending order. We don't care. It'll be forced upon it once we decide which side it goes on. Does that make sense? Like, we don't have to worry about the order because it'll be forced upon the side that we're talking about. How would we find the combinations that make sure the numbers to the right would be descending? That's the thing. We don't need to care. What we need to more importantly is we're deciding where the numbers are going. After that, I don't care where they are in that side. basically what we're trying to do is we're deciding whether it goes onto the left or to the right of 15. After that, don't particularly care. Because you're going to, once you're chosen aside, you are going to be forced into a certain position if it wants to remain a mountain sequence. Does that make sense? So like, for example, let's say that this here is, so let's kind of like imagine it for a second. Let's imagine this so it can help you. So so who do you want to be to the right of 15? Who should be to the right of 15? Or to the left of 15, I'm sorry. In this case, who should be to the left of 15? Like, it doesn't matter who you pick. What do you want this value to be right there? What's up?
16.
16? Well, there's not a 16. We can't go any higher than these values here. Your values only go up to 15. Not really, I understand how 14 No, so because think about it this way. Once you pick the side, well, here, I'll show you. Well, it's better to show rather than tell, actually. So what I'll show you is this. So all I want you guys to do is literally just tell me out of the first 15 positive numbers, what, not including 15, what number should be to the left of 15? Okay, so let's say 13, right? Now, we know that, so as an example, let's pick, let's pick 13 to go to the left. Right? So we agree that 13 is to the left, and then we hit 15. Now, where does everyone else go? Everyone else goes where? Goes to the right. Now, where should 14 go? To the right of 15, yeah. But no, so okay. So what I want you to notice is you just told me it needs to go in directly to the right of 15. It does not have a choice. It must go right after 15. Does that make sense? Because if we have it in any other position, then it's not in complete descending order. Basically, yeah. There's like not necessarily like yeah, kind of basically. There's only one path to complete this if we want this to be done. Because otherwise we're kind of screwed. Like exactly. Because that's where the freedom of choice is, essentially. Once we know who's to the left, everyone else kind of falls into place. Does that make sense? Yeah. So again, it's really more so we're trying to choose where the numbers fall, not where the numbers like what position they get into, essentially. Okay, so now we do that for 15 when it's in position 1. So now in position 2, how many ways can we pick the numbers that are ascending? If 15 is the third number in the sequence, how many numbers should precede 15? If 15 is in position 2, like it is right here, how many numbers go before 15?
Two numbers.
2 numbers. Yep. So you have to pick 2 out of 14 numbers to that so it can ascend, of which there are 14 choose 2 ways to do that. So notice we have a 14 choose 1, we have a 14 choose 2. We can kind of wash, rinse, and repeat that for every other position. And so that's where I get these guys here. where I include position 0 and position 14. The reason I add all these values up is because they are mutually exclusive. You can't have 15 in multiple spots at once. Make sense?
So we pretty much have to start off at position 0 and then move down the line, right?
Because you're trying to account for everything. Yeah. We're trying to capture every single scenario that could ever imagine. Yeah. So
And
this
then not including the highest number, right?
we'll include it when it's at the end and at the beginning.
Okay.
We'll include it for the sake of our argument, just so we can make it as easy as possible to understand. So right now we just run through all the positions that it could run like possibly be and make a mounted sequence based off of that. Does that make sense?
Yeah.
And so now we get this. So I just turn it into a summation because that's what this really is. And then all I did is just use what is called the binomial expansion formula to get 2 to the 14th. Does that make sense or not really?
Yeah.
Okay. So TLDR is basically, hey, add all these values up, made a summation out of it, did a little math wizardry and just attached a bunch of ones because why not? Then use the binomial expansion formula and got 2 to the 14th. Does that make sense?
Yeah. On the exam, are we gonna have to write out how to do the summation and
Uh,
then get to 2 to the 14?
like this 2 to the 14th one?
Yeah.
We would like to see how you got there for partial credit. But if you tell me 2 to
Okay.
the 14, like there's multiple ways you could get this. But like this is just one of them.
Okay. All right.
Yeah. But 2 to the 14th is not the final answer because the problem is where can 15 not be located? Where should 15 like not theoretically be?
Position 0.
It can't be in position 0 because it can't start. Where else?
And last position.
The last position, position 14. That's being represented by 14 choose 0 and 14 choose 14, which both of which evaluate to 1. So you need to take away 2 from 2 to the 14th. Punch it into a calculator, and we get this answer. Make sense?
Yeah.
Any questions on how I did that one? Can we go? Okay, so we'll go over the revision question, and then yeah, we can go over the and question and afterwards. Which question in the revision do you want me to look at? I was just wrapping it up in those one before I started my video. What question do you want me to look at? And that's 6. What is 6? Oh, this one? Yeah. So the number of positive integers where n is between 1 and 1,000 and n cannot be the square or cube of an integer. Okay. So I want you, how many numbers are between 1 and 1,000? If you're including 1 and 1,000, how many uh are there? Yeah, there's 1,000. Basically, how we're going to do this is this. A number is either going to be a square or a cube, or it's neither of those. Do you agree that these are kind of like opposite events? So square, cube, and not square or not cube, not square or cube is opposite events. Does that make sense? Yeah. The idea is that because these are opposite events or they're mutually exclusive events, meaning they should not be happening simultaneously, we need to add them together. Does that make sense? So the number of ways we can make a square, the number of square or cube integers plus the number that are not square or cube needs to be equal to 1,000. Does that make sense? Because that's how many total integers there are. So far so good. And then once we do that, we just need to figure out how many integers are either square or cubes. Once we do that, take away that from 1,000, and then you're good to go. So far so good on how I'm approaching this problem. Alright, cool. Okay, so now we need to figure out how many are square or cube integers. This is what we call inclusion exclusion. Basically, we want to find the number of squares, perfect squares, plus the number of perfect cubes, and then we need to subtract out how many are perfect squares and perfect cubes. Does that make sense? And then after that, it's just a matter of kind of like brute forcing. So I know for perfect squares that are less than or equal to 1,000, start at 1 squared and go all the way to 31 squared. So from the first 31 positive integers. So the first 31 positive integers, when you square them, they're less than or equal to 1,000. So that's where I get 31 numbers. Do the same thing for cube. It goes all the way up to 10 because 10 cubed is 1,000. And then locate the ones that are both perfect squares and perfect cubes. That would be 164 and 729. And so if we put this all together, we get 38 perfect squares. Yeah, we can do some brief probability in a bit. So we can get 38 that are perfect squares or perfect cubes. And then from there, we just plug it back in and get our final answer. 962 integers are neither a perfect square nor a perfect cube. At least that's what I got. The revision key, I am still trying to finish it. But I was going to upload this one here because I just like got as much as I could out of it. Yeah, no worries. Okay. What other questions do you guys want me to try? The ant problem? What was the ant problem that I even gave? I literally don't even remember. Is it this one here? Yeah, okay. So let's think about this one for a second. So first, how many ways can the ant get from 00 to 2017? Yeah, it should be given to you guys during the final. Yeah, no problem. Okay. So how many total moves must the ant take? Okay. So we know he has to take 37. How many of them are up movements? Those are right movements, not up movements. Yeah. So it would be 17. Yeah, 17 of them are up movements. So how many ways can we choose 17 movements to be up out of 37 total moves? So if we want to, yeah, it's 37, C37, 17. Does that make sense? Yeah. Why? Because we don't so think of this as like we have 37 moves, total moves, out of those total movements, we need to take 17 of them to go up. We do not care when the ant moves up. It's just that he executes 17 up movements. We do not care when the ant executes his up movements, that is the indication of combinations, which is why we are using a combination formula. Does that make sense? Why are we using combinations? We are using combinations because it does not matter how the ant completes his movements. All that we care is that he gets to his endpoint. Does the order matter? Does the order matter? Even if the movements vary from path to path, ask yourself this: is there any importance in that? At the end of the day, are you changing anything about the total movements that you have to take? Are you changing any amount of up movements that you have to take? Probably not, because think about it like this. Once you execute 17 movements up, you're not going anywhere up, farther up. If you keep going up, you're not going to hit 2017. Does that make sense? So it doesn't matter when you do your up movements, just that you do. Makes more sense? And if order doesn't matter, that's the biggest red sign of a combination. Nope, you're going to have to deduct that on your own. That's something you have to deduct on your own, whether order matters to a problem or not. In here, it's kind of vaguely implied that, yeah, it doesn't matter that order doesn't matter because one path doesn't have higher precedence than the other. What's the tell here for this question? Is there any mentioning of when you need to execute your movements? The biggest hint I can give for combinations versus permutations is if you are being asked directly, is there an order of importance in your movements? Do I care when the movements occur here? Or do I care that they just happen? Notice here, like, I'm not saying it, like, I care that he doesn't hit this point 13.6. But like after that, I could care less how he gets to 2017. Just get there, period. Just get there without hitting the point, right? I don't care if you have to go right 20 times and then go up 17 times, or if you go right once, then up 17, or whatever you want. You just need to get to 2017 without hitting 13.6. Makes more sense? Yeah. Any array of 17 up steps will be okay, as long as you have 17 up steps. Yeah, what they differ in the selection of when they occur, but ultimately it won't matter. So now that that's known, this is this account. Oh, come on. This is when this value assumes we can walk anywhere. So that's just a slight problem about this. This is the total amount. This represents the total amount of ways to get to 2017. Does it make sense? So that's a total amount of ways to get to 2017 with no restrictions. But we can't just walk anywhere we please. What is the point that we cannot hit? Like, where's that point being located? So where is the point that we cannot hit in this problem? In here. Where can the ant not run into? Um, why are we not factoring in the 20 in our calculations? This does factor in 20. Remember, this is the same thing as saying C 3720. They're both the same. And yes, it is 13.6. You're correct. The reason that these two are equal is, think about it like this. What's 37 minus 17? Okay. What do you think that 20 happens to represent? So once you pick when the 17 moves are happening, don't you automatically pick when the X movements are happening? The remaining 20 moves have to be happening. Because once you automatically know when you're going in the Y direction, you should automatically know when you're going in the X direction. That is the same thing as this thing here, where we decide when when the X movements are happening, and then our Y movements would automatically be decided. Does that make sense? So what we're doing here is we cannot hit the point 13.6. So what we want to do is find the number of ways we can get to 2017 by when we also, how do I want to say, when we get the number of ways we can get to 2017 while also crossing 13.6. This represents the number of invalid ways to do our problem. From there, what we're going to do is we subtract this value from C 3717. Does that make sense? What we're going to do is literally, okay, now we're going to try to get to 2017, but now we also want to get to go through 13.6. Once we figure out how many ways we can do this, take that value away from here, and we will find our answer. Just to be sure, the C of X plus Y, comma. No, it's not, no, those are not usually the same. In general, it's that C of N, comma, K is equal to C of N, comma, N minus K. That's the one you're thinking of. And so what we end up doing here is first, yeah, so first we need to find the number of ways we can get from 0, 0 to 13.6. We're gonna need that off the top of my head. This takes a total of 19 moves, because 13 plus 6 is 19, 6 of which are going to be up limits. So there are, I believe this would be 19, choose 6 ways to get from 0, 0 to 13, 6. So, so far so good on this. Any questions on how to do this? Okay. And so what we're gonna do after that is now finish the path by going from 13.6 to 2017. Does that make sense? So this will take a total of 18 moves to do. And this is because 37 minus 19 equals 18. And that means there's going to be 11 of which are up limits. Which is because, and that is because 17 minus 6 is 11. Okay. And so that means there are basically, oh gosh, 18 choose 11 ways to do this. Ways to get from 0 or 13.6 to 2017. Cool. Any questions on how I got this one? Any questions on how I derived this? Okay. So now we have that. We're gonna say now we're gonna multiply these values together since they are independent of one another. And so the total number of invalid ways is given by this product, which I'm too lazy to do. So it's 19 choose 6 times 18 choose 11. So, oh gosh, this is going to be long. So the number of valid ways is going to be given by the following. We're going to take this C3717 because I'm too lazy to write it. C3717 minus this product. That's what I'm looking for. Okay, there we go. And yeah, that's how I would have done that problem. For number 3 on revision. No, that's not the one. Other one. Nope, that's a mountain problem. It's induction. The 3 factorial and the 2 factorial. Oh, okay. Reason the 7 fact basically how many ways can you permute how many? Oh, I was not counting. Oh my god. Jesus. It should be 8. Yeah, 8, but that's the only thing. Sorry. It should have been 54. Oh no, there's 9 letters. God damn it. 9 letters. I can't count today. That's what happens when I speedrun that problem. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, that's a 9. Should be 9 factorial. Um, as for how I got 3 and yeah, that's the only thing. Yeah, I just counted that wrong. Sorry. It should be 9 factorial. Other than that, it's the same thing. Whoops. I feel stupid. Um, but yeah, sorry, I sped run that too fast. Um, any other questions you guys want me to kind of like try? Mhm. How to recognize overcounting and how to fix it? Um, varies from problem to problem, but typically, a good example is here where if you have multiples of the same object running around and you have to reorder them, if you have to reshuffle multiple letters that or multiple things that are of the same type, that's a good chance you could be overcounting. As an example, here in this word databases, what happens if you swap the A's around? So let's say, so in this, right? So when we're talking about databases, uh, one permutation, would you agree one reordering is database? Like you could keep it as is. Does that make sense so far? Okay. What happens if you swap the A, the A's? Yeah, same thing, right? Well, that's a problem if that's a problem because permutations would count this swapping as uh different different orderings. Does that make sense? Basically, what it's saying is like this databases is not the same thing as this databases, like according to permutations. Does that make sense? So if you swap those A's around, it apparent permutations would say, hey, that's a different orientation you just made. Obviously, that's not the case because databases is the same thing as databases. So when you have multiple variations that represents the same thing, that is a massive red flag that overcounting is at play. As for how to fix it, it depends on problem to problem. In this problem, it because every reordering kind of has a problem of overcounting, then we would need to divide because everyone has a problem of reordering. Other problems, not all of the orders have variations. So it honestly, like the best I can say is it varies from problem to problem. Does that make sense? Yeah, what's up? Uh-huh. But instead of it being a range, we're counting the number of possible strings for this word with for possible sizes. But instead of range, Okay. So what is your definition of a string? Is it like a CS string or is it like an actual word I can find in the dictionary? Because if it's the word in the dictionary, that's really tough. Like, what do you mean possible strings? Just letters and strings, not okay. So are you asking how many different variations I can make? Are you asking how many different variations? So we count the letters, count all the possibilities with one letters, two letters, and so on. So are you saying like, okay, so we're taking databases. What do you mean by one letter, two letters, and so on? I'm trying to understand that part. So possibilities would be D, DAS, DASA. Um, e- so are you saying, okay, so taking databases, so if I take the word databases, how many different like total strings I can make? With length 1, 2, 3, 4, 5, 6, 7, 8, 9. So in this we'll use we're forced to use auto letters in the arrangement. Yeah. So it would turn into like a really shitty counting problem. You would have to do the number of total ways you can do one string, then two strings, then three, then four, five, six, seven. That's even harder than this problem, like really hard, because that basically means you're doing like 9 different counting questions, each of which are like could have a possible different technique in what they do it. Like if I'm just like thinking about it, like I don't want to think about how many ways you can do databases. I think it's only like DASTBE, so like 6, and then yeah, like that would be really hard essentially. Like you would have to like do it scenario by scenario, essentially. Does that make sense? Yeah. But you would have to like sit and do all of them. But yeah, any other questions you guys have for me? Any other questions you guys like want me to try to do? Uh, this one. Okay. I can't, so I can't draw on this computer, which is like incredibly depressing. So like the graph is going to be kind of tough. I'll just have to describe this in words. Basically TLDR, uh label label the rows and columns as described above. So and then ones represents an ordered pair that is in the relation. So zeros is not included. So what is who's in this set? Essentially, like where would be an example of it? Like what would be an order pair? Yeah, A comma B. We would need the order pair A comma B. What else? Yep. C D. Where else? D E. Yep. D G. I agree. Where else? Yep. E F. Where else? Yep. F D. What else? G H. And yeah, H A. Yep, that's all of them. And basically, to draw the diagram, the directed graph, create 9 points, we'll call them points. A through H, basically. A through H, and for each point, for each ordered pair, draw a arrow from the x coordinate to the y coordinate. That's it. That's all it is. Nothing more than that. So you would draw an arrow from A to B, an arrow from C to B, and so on and so forth. Does that make sense? Not a problem. All right. So as with number 9, so let n be a positive integer with n greater than 1. Oh, not that one. Which one am I looking? Oh, from the sample exam. Oh, whoops. Other one. Blah, 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 blah. This one. Okay. So Charlie has 10 different pairs of shoes. She's got to pick 8 of them at random. What's the chance that she gets 3 matching shoes? Leave your answer as a fraction. Okay, so let's think about this one for a second. So you have so first she has to pick 8 of the 20 shoes at random. How many ways can she do that? Let's start with that. Not just 20. You need to take for Shelly needs to take 20 out of 8 out of 20 shoes, take 8 of them. How many ways can she do that? With no other restrictions. Yeah. C 20 comma 8. Yep. So your sample space, the denominator, which is the denominator is 20 choose 8. Does that make sense? Now you need to figure out how many ways she can take 3 pairs of shoes. This is going to be obviously your numerator. Does that make sense? So what we need to do is first, which 3 pairs did she take? How many ways can she grab the 3 matching pairs? Well, there's 10 different pairs of shoes, and you need to grab 3 of them. So there are 10 choose 3 ways you can grab the 3 matching pairs. Does it make sense? Now, we need to keep track of how many shoes that she needs. Once she grabs these 3 matching pairs, that is 6 shoes that she has grabbed. 6 out of her 8 shoes that she's grabbed. So there's 2 remaining shoes that Shelly needs. Make sense? Okay. Now, keep in mind, these 2 shoes should not be matching. If they are matching, then we're not solving for 3 pairs, we're solving for 4 pairs. So because we're in a situation where we need 3 pairs of shoes, we need to have it so that these 2 remaining shoes should not be matching. Does that make sense? Now, keep in mind, there are 7 remaining pairs. The 7 that she didn't grab when she did her little matching pairs game earlier. If these remaining shoes should not be matching, Shelly needs to grab from 2 of the 7 remaining pairs. Out of 7 remaining pairs, she needs to yank out 2 random pairs to look at. Does that make sense? And you can do this in 7 choose 2 ways. Go so far? Now, she knows what pair of shoes to take, which pair she's looking at. Which shoe in the pair is she taking? Is she taking the left shoe or the right shoe? So the first pair, she can only grab one of the shoes. So either the left shoe or the right shoe. So there's 2 ways to do that. Same thing with the other pair, with the second pair. Grab either the left shoe or the right shoe. Does it make sense? And now to put this all together, every single event that we describe, which is the 2 of the 7 remaining, the 10 choose 3, the 2 choose 1, 2 choose 1, those are all independent events. Make sense? Since they're independent events, we're going to multiply them together. And so she can pick exactly 3 pairs of shoes in that many ways. So that's our numerator. Just put it all over a fraction to get our probability, which is what we wanted. Why divided? Probability. We're talking about probability. So there's going to be division. You are counting the number of favorable outcomes divided by the total number of outcomes. CC. E. Any other questions you guys have for me? I already posted it here. I'm gonna try to post like multiple. I'm gonna keep trying to work on it. From my file. Oh, it's in my it's under the announcements. Just look for the one that's right here. Can we go over number 1 from your final practice? Yeah. Is it this one right here? I'm guessing this is the one here. Yeah, no worries. TLDR, basically here's the TLDR, 26 times 25 to the 9. That's how many ways. So that'll be that. Okay. Yeah, no worries. We'll kind of talk about how we get that a little bit later. Any other questions you guys have for me? What you guys like want me to kind of like discuss? Turn from vision. This one here? Okay. So you're given a directed graph, and you want to figure out if they're reflexive, if it's reflexive, symmetric, anti-symmetric, or transitive. Okay. For reflexive, uh, does every node loop back to itself? If yes, then it's reflexive. Done. Does that make sense? Any questions on that one? Cool. For symmetric, let's see. Um, oh, yeah. Okay. So we have let's say we have 3, 4. Does that make sense? Because you have a arrow that's going from 3 to 4. Do we have 4, 3? In other words, yeah, in other words, if there's an arrow going backwards. No. So not symmetric. Yeah, this is not symmetric. For anti-symmetric, um, do we have, let's see here. Does one, do we have the inversion of 1, 4, 3, 1, 3, 2, and or 4, 3, or 3, 4 in our relation? Do we have any of those? Like basically invert any of these pairs and see if you can locate a arrow. They're arrows. So if we invert 1, 4, that should be 4, 1. Doesn't look like there's a 4, 1. If we invert 3, 1, we'll have 1, 3, but we don't have 1, 3. If we have 3, 2, if we invert 3, 2, then it should be 2, 3. Don't have 2, 3 either. And then finally, 3, 4. We would need to have 4, 3, but we don't. So this is no, none of these exist, none of them. No, you need to invert all of them. You have to invert all of them. So our relation is fine to be anti-symmetric. So basically what we're doing is as long as they're not equal to each other, as long as the x and y coordinates are not equal to each other, invert your coordinates and see if you can find it. It should be the case that none of these exist. None of their inversions exist. Does that make sense? What's transitive? Transitive is if A comma B is in R and BC is in R, and so too is AC. Basically, if A equals B and B equals C, then A equals C. Yep. Is this transitive? Long story short for this one, yes. Yes, because how do I want to explain this? Yes, because there is no ridge in this graph. We'll call it a bridge. Yeah. Basically, yes. There's no bridge in this graph. I.e., there is no instance in where both A, B, and BC is in the relation for any value A, B, and C. Yeah. So basically, there's no bridge in this graph. That's meaning your A, B, and B, C are your bridge, and they never exist simultaneously. Any questions on how I did that one? Any other questions you guys have for me? Um, yeah, I can explain it in a second. Just wanted to read this for a second. Oop. Number 4 on which question? Like which number 4? And that's this one here? It does pseudocode stuff here? Okay. So there's 3 parts to it. Basically, so when we're for part A, just like evaluate this code. So think about it like this: when I is at its first iteration, what is the value of sum? So, how do I want to explain this? Do you know how a for loop works by any chance? Or like a nested for loop, essentially. Okay, so when I equals 1, you have to finish an entire instance of J, this entire instance of J. So when I is equal to 1, then we go to J equals 1. What is the value of sum when J is equal to 1 here? So like when J equals 1, what does the sum become? What does that sum become? So think about it like this. When J equals 1, the sum increments by 1, so your sum should be 1. Then J equals 2, so now the sum is equal to 1 plus 1, which is 2, and then so on and so forth. So by the time this first inner loop is finished, your sum is 5. Does that make sense? Because after every inner loop, your sum goes up to 5. Then I increments to 2, and then you do the whole thing over again. So now it goes 5. So now you start at 5, then you go 6, 7, 8, 9, 10. And that'll finish the second inner loop. Basically, every iteration of I increments the sum by 5. Does that make sense? And so after all 10 iterations of I is completed, you get a sum of 50. Does that make sense so far? Any questions on how I did that? Okay. When we change the inner loop from 1 to 5 to I to 10, the first iteration, on your first iteration, J will run from 1 to 10. So your sum will equal 10. Does that make sense? Since the inner loop runs 10 times. Does that make sense? Then when I is equal to 2, now the inner loop will only run 9 times because it goes from 2 to 10, not 1 to 10. So it'll be 10 plus 9, which is 19. Then when it's 3, 10 plus 9 plus 8. And so you can see where the pattern's going. Kind of. So the total, it's still, so when I equals 1, it runs 10 times. And then as I increases, the number of iterations for J decreases. Oh, for this one here, right? By the time it runs. Yeah. Yeah, basically. If we're talking about part A, then yes. Does that make more sense? On which part? Which part are you confused on? On what which part are we doing? Are we doing part A or part B? Are we talking about part A or part B? Part A? Okay, so if we're talking about part A, the first for loop. Yeah, the first for loop runs 10 times. Yeah. And then the second for loop runs 5 times, will run 5 times. Well, for every one of your iterations, like every iteration of I, your inner loop runs 5 times. So when I equals 1, J runs 5 times. When I equals 2, J runs 5 times. So on and so forth. So in total, you basically run a iteration like 50 times, essentially. So we increment the sum by 5, and so after all 10 iterations is done, the value of sum is 50, because that's what happens when we sum by 1 each time. Does that make more sense? No, sum is 50. Sum is 50. J will never go past 5. All I'm saying is that this entire thing just runs 50, like sum just gets up 50 times. It's pseudocode. It's not any language, it's just pseudocode. You can program this in anything you want. When I was doing it, I programmed it in Java. Like I just programmed this in Java using Eclipse. It doesn't want to load right now, but it oh, there we go. Here, let me show you. So come on, ID. So like what I did is just I just implemented the code. So in Java, this is what the code would look like. And if we run this, $50, yeah. Then you go on and on. Does that make sense? Do the same thing here, just slide modifications, and then try to generalize it. More sense. Any other questions you guys have for me? How would I come up with the formula? Honestly, I tried to come up with that. I'd rather write a method. I just wrote the method, just like, hey, it's n plus n minus 1 plus n minus 2, and just going with that until you finish all your iterations. I was trying to come up with some like summation formula, but like I lost time. I was running out of time for the summation formula, so I'm sticking to just a method for now. Any other questions you guys have from me? This guy? Okay. So this is going to require a couple of ideas of sets. Basically, how I did this, you have your size of the universe is 12 elements. Now, the size of the union is 8 elements, and the size of the intersection is 3 elements. Does that make sense so far? Up to this point? Basically, we're just saying like, hey, this is how big each set is. So the universe is 12, has 12 elements. A union B would contain 8 elements, and A intersection B would contain 3 elements. Does that make sense? So what we're doing is a couple of things. I want you to note that the complement of A union B is just A union B with a big ass bar. And then the complement of A intersection B is A intersection B with a gigantic ass bar over it. Which is basically which is what you and if we use De Morgan's law, this is what we get. Not A union, not B. Does that make sense? So far, so good on this part here. Yeah, the bar means not. It's not in set language. Does that make sense so far? Any questions on that? Okay, so what we're gonna do is basically, because you know how many sets are in A union B, and we know how big the universe is, we can figure out how big this set is, because it's just 12 minus 8, which is just 4 elements. Same thing with the other set. We can find out that this has 9 elements. Does that make sense so far? Or not really? And so far so good on how I got each of these sizes. Obviously, this was given, and then this is just through a little bit of math wizardry through 12 minus 8 and so on and so forth. So, okay. Now, what we're going to do is we're going to utilize this part here. Utilize this. Basically, because we know that this set here, or basically this complement of A union B, because this is a subset of D, I can say with certainty your set D has to have 4 elements. The reason why is because the complement of A union B is a subset of D. Every element in this set must be in set D. So at bare minimum, there's got to be 4 elements in set D. Does that mean make sense?
Where can you just say that again?
Yeah. So you see how you see this gigantic? You see the complement of A union B?
Yeah.
How many elements are in there? How many elements are in this set here?
Not sure, but yeah.
Well,
Not sure.
so remember, there's 12 elements in our universe, right?
Okay.
Now, how big is A union B?
8.
8, right? So
Mhm.
if I want the opposite of him, just find how many elements are left when I do 12 minus 8.
Oh, so you're getting rid of it. Okay.
Yeah, getting rid of the ones that are in A union B. Everyone else that's not in A union B is obviously in this set. Does it make sense?
Yeah.
So there's 4 elements that is in this set right here. Does it make sense?
Correct. So, okay. And then the D part
Mm-hmm.
on the after it says satisfy A union B not.
Yeah, so the non-A union B is a subset of D. Remember, in order for something to be if A is a subset of B, so if I say in general, remember, if I say that A is a subset of B, right? If I say this, that means every element in A must be present in B. Does that make sense?
Okay, so all the elements in A and with all the elements in B as well.
Yeah, any element that belongs in the left set must belong in the right set. So any
Okay.
elements that belongs in this set here,
then-
the complement of A union B, it's got to be present in D.
Okay.
Does that make sense?
Okay.
Hence why, at bare minimum, I can guarantee without a shadow of a doubt, D must have 4 elements, bare minimum. Does that make sense?
Yeah.
And now we want to probably try to find the maximum amount of elements. The way we do that is by leveraging the definition of set difference again. Remember, every element in A must be present in B, right?
Mhm.
No more, no less, right? So you cannot exceed however many elements are in the right set. Does that make sense?
Okay. Yeah.
Well, we know that right set, complement of A union complement of B, has 9 elements. That's what we calculated here. Does that make sense?
So, hold on. How did you come up with that? You said the size of not A union not B.
Because that's the opposite of what that is the complement of the intersection between A and B. Does that make sense? Because it's like the polar opposite of this set, like the absolute opposite of this set is if I just drew a line over the entire set.
Oh, okay, okay. I see.
So,
Okay.
so like what I'm saying is like polar opposite of this set, then use De Morgan's to get here. Does that make sense?
Yeah.
So if I want to find out how big this set is, same thing I did here. 12 instead of 12 minus 8, do 12 minus 3, which gets us 9 elements. Does that make sense?
Yeah.
So now you know that this set here has 9 elements. So because D is a subset of the set here, D cannot exceed 9 elements because D is a subset of this set here. Make sense?
Mhm.
So you know at bare minimum it has 4, at maximum it has 9. How many elements are left up in the air?
So if D has 4 and the other
The-
one has 9.
Well,
would
no,
you
these are
make-
the same sets. These are the same sets. We're saying D has at bare minimum 4 elements, and at its best, D can have 9 elements.
Okay.
So if you know he has 4 elements guaranteed, how many elements are left up in the air?
Oh, you mean 5. Okay, okay, I see.
Yeah, we're left with 5 possible elements that they can contain. Does that make
Okay.
sense?
Mhm.
Each of those 5 elements that are up in the air have 2 choices. You put it in set D, or you don't put it in set D. Does that make sense?
Yeah.
So, and so you have 5 2s running around. That gives us a total of 2 to the 5th, which gives us 32 sets.
Would you mind uploading that on Discord?
Yeah. Oh, I already uploaded it.
Oh, okay, sweet.
Mm-mm-mm-mm. Any other questions you guys have for me? Okie dokie. I'll be. Yeah. Yeah, and I'll post the solution key and talk about it there as well. All right. Just let me know if you guys need anything, and I'll be around tonight to help out. Oh, shoot. Actually, is it okay if I just call you in Discord and I'll just talk about it there? Yeah. Just send it to just message me on Discord when you're ready. Yeah, like that's the thing. It's a lot of these remember, a lot of this is like we say it's not cumulative, but as you see here, if you don't have not prior knowledge of some of the previous units, it's a little bit tough, unfortunately. So it's while it's not cumulative, it is kind of quote unquote cumulative. But I'm gonna still be around tonight to help. So let me know if you guys need anything, and I will see you guys on the next one. Until then.